This tutorial will look at calculating the load bearing capacity of piles, and in part 1 we're going to be looking at piles in sand only sand. In part 2 we will cover piles in clay. The calculations vary just slightly, so it would be best if we break it up into 2 parts. The total resistance a pile provides can be split into a few components. So let's just give ourselves a little pile here in the ground. If we have the ultimate load capacity of the pile acting down here, we call this PU. If we have the ultimate resistance at the base of the pile, PBU, acting upwards, PSU acting at the sides of the pile, which is the ultimate resistance, the ultimate shear resistance on the pile shaft, and W acting downwards, which is the self weight of the pile. So from the diagram, using the directions of the forces, the capacity of the pile comes from the two components: friction between the saw and the surface area of the pile, and the resistance or reaction at the base of the pile. And using the directions, we can say that PU is equal to PSU plus PBU minus W. So we have the ultimate load capacity of the pile equals the ultimate side shear resistance on the pile shaft plus the ultimate resistance at the base of the pile minus the self weight of the pile. Rather than me go through a great big long list of equations to use for determining load capacity of piles, I think it would be best if we work through an example. So let's take this example here. We have a pile 11 meters deep, 0.6 meters in diameter. We're looking at a circular pile here. We're saying that the unit weight of the saw it is in is 19 kilonewtons per meter cubed, and the internal friction angle of that saw is 27 degrees. And remember, we're looking at a sand. Now our question is to determine the ultimate load capacity of this pile. So let's start with the base resistance. PBU, the base resistance, is equal to AB times, in brackets, FB plus P naught. Now, AB is the area of the base, the cross-sectional area of the base. FB equals the net ultimate resistance per unit area of the base. P naught equals the overburden pressure at the level of the base. FB is calculated by NQ times sigma V. To determine NQ, we use this graph here. We can use our internal friction angle 27 to read off a value for NQ, and we have here, if you get something slightly different, doesn't matter too much, but I'm reading off a value of 18 here. Then we can go on to calculate our sigma V. Sigma V is simply the unit weight times the depth of the pile. So that's 19 times 11 equals 209 kPa. So our FB equals 18 times 209, which equals 3,762 kilopascals. AB, we can work out the cross-sectional area of the base, pi r squared, so pi times 0.3 squared equals 0.28 meters squared. P0, the overburden pressure at the level of the base, is the same as sigma V. So we've already calculated that, which is 209. So all these numbers now that we've worked out, we need to put it back into our equation for PBU. PBU equals the area of the base, which is 0.28, multiplied by brackets FB, which is the net ultimate resistance per unit area of the base. We calculated that 3,762 plus P0, overburden pressure at the level of the base, 209. Close brackets, and then we will get an answer of 1,112 kilopascals. Now that we've got the base resistance, let's calculate the shaft resistance. Our shaft resistance, PSU, equals AS times FS bar. Now FS bar is the average ultimate side resistance per unit area. The bar just representing average in a symbol. AS is the surface area of the pile shaft in contact with the saw. We don't use the base or the top of the pile because the top of the pile isn't in contact with any saw, so there's no resistance provided there, and the base is taken into account separately as we've done earlier. So it's purely the area of the pile, or in this case, because it's a circular pile, we're looking at the curved surface of the pile, that surface area in contact with the saw there. So our AS can be simply calculated as 2 pi times r times L, and that will give us the curved surface area of the pile. So 2 pi times 0.3 times 11, and that will give us 20.74 meters squared. Now we need to calculate FS bar. FS bar is equal to NQ divided by 50 times sigma V effective times tan times the internal friction angle. Now we said we needed the average. So we need the average vertical effective stress. Why do we need the average? Well, because we're looking at the resistance of the shaft, provided by the shaft of this pile over the whole depth from 0 to 11 meters deep. Now, the vertical effective stress at 0 meters is obviously 0. At 11 meters, it is 19 times 11, which we calculated earlier, which is 209. Now, the resistance that the shaft provides is not constant throughout the whole length of the pile. We're going from a minimum of 0 all the way to 209 at the bottom, and we want the average, so we can simply do that by 209 divided by 2. So let's go back to FS. We got our NQ value earlier as 18, so we can do FS is equal to 18 divided by 50 times 209 over 2, which is our average vertical effective stress, times tan times 27. That will give us an FS bar value of 19.17. Then our PSU will equal 19.17 times 20.74, and that will equal 397.4 kilonewtons. So let's go back to our original equation. We had Pu equals PBU plus PSU minus W. We've obtained our value for PBU, which is the base resistance, and that was 1112. So we have Pu equals 1112 plus our value of PSU, which was 397.4. Now we need to minus W from this. W is equal to the weight of the pile. Now this might work differently for some people, but the way I was taught is if the unit weight of the concrete is not specified, then you just take it as to be the same as the unit weight of the saw. Now the unit weight of concrete is normally 25, but in this case we're going to say it's 19. Why you do that, not entirely sure, but it's up to you. The process is still the same, it's just different values. So in this case then we're just going to take the unit weight of the concrete to be 19. So we're saying that the weight of the pile is equal to 19 times pi r squared times the length L, and obviously pi r squared times L gives us the volume. So the unit weight times the volume will give us the weight of the pile, and that will give us 59.1 kilonewtons. So let's put that back into our Pu equation, and we'll obtain a value for the ultimate load capacity of the pile as 1450.4 kilonewtons. Okay, so we've just determined the ultimate load capacity of a pile in a sand. It works slightly differently, as I've said, for piles in clay, and we'll be looking at this in part 2.